Hello everyone, this is MEHUL and I will be presenting my slides on interactive graphic display system. And this system is a very minimal graphic system that is using both two modules, that is ETKB and ETGLCD module with on the 8085 trainer kit using both the PPIs. The motivation of this project is simple, that is to make a very small interactive graphic system, and the system is a very basic slide show system that right now, as of now, only presents two slides that are saved in the the 8085 trainer kit RAM. In the system, the user presses the ETKB module key, interacts with the 8085 with the ETKB module, and input is processed, and based on that, on the GLCD screen, the output is shown. Moving on to the objective, as I told you before, a very basic GLCD based graphic system, and operation is office, as I told before in the previous slide. So talking about the system overview, the hardware we have used here is the 8285 trainer kit only, and then considering the ETKB module we have used, and also the ET-GLCD module, which is divided into 128x 64 pixels, which uses two interacting KS based modules. Okay, and two 8255 PPIs which are interacting with, where one is interacting with the ETKB module, that is the keyboard module, and other is interacting with the GLCD. We will talk about how GLCD works and ETKB module works in detail in the further slides. And basing on talking about the operating idea is simple, that the 8085 sends the keyboard module that's corresponding interactions through the 82552 path, and to the GLCD on the 8251 path. Okay, moving on to the next slide. I have set up here a very basic hardware architecture block diagram so that we can set up a good context here for the future slides. Here you can see that both 82551 and 82552 are configured here to interact with GLCD and ETKB module. Unlike our lab practicals where we only interacted with 82551 using port A, here we will be interacting with J1. We'll be interacting with both PPIs, 8255 PPIs, through port J1 and J2. This was done to avoid complex time multiplexing logic inside the 8085 CPU, where one single port is used to multiplex, and even this would require a hardware connector, Y-based connectors, which would also bring us other problems. So here we are interacting with two 8255s that gives us a better decision logic and simpler code control and program control. Talking on the right side of the diagram, we can see that 82551 is interacting with GLCD, and this is only both the ports, port A and port C, are configured as output ports because there is nothing to read from the GLCD module. The port A is responsible for sending GLCD data, and port C is responsible for sending GLCD control words, controls like enable, RS, read write, and etc. Which we will be talking in later in the slides. The ETGLCD module is a 128x 64 pixel screen, which is actually divided into two 64 cross 64 controlling models, that is the KS1. Now talking on the left side, here the keyboard module has double arrows. You can see that 8085 interacts on both direction, bi-directional order. The port A is responsible for sending, port A is responsible for reading the key, and the port C is responsible for row select. The logic here is that the 8285 sends the active high signal on port C that passes on to the 80 kb module, and when a key is pressed, that is read from port A and passed on to 8285. Okay, so we move on to the next slide here. As I talked in the last slide too, that why have I used 8255 PPIs, two 8255 PPIs instead of one? As I told before, to avoid complex decisional logic and not also avoiding time multiplexing. And using two 8255 PPIs was actually easier and allowed us to divide both the input and output logic concurrently within the 8085 decision logic. Also, the dual arrangement will be very practical and visible once we move further in the slides. The role of 82551 is to interact with the GLCD using RS, RW, EN, CS1 and CS2 controls. The CS1, 2 and CS1 and CS2 controls are chip select 1 and chip select 2 because they are two chips that control the GLCD module. CS1 is responsible for interacting with the left 64 cos 64 half, and CS2 is responsible for the right half. Port A is used to send the 8-bit display data, while port C is used for the control word generation and latching logic. For the functions performed, the GLCD initialization, command transfer, and using the 8255 the page and column selection and all the data writing logic, that is data office. So here's a very basic simple diagram that you can see. The 8085 writes on out03, that is the control word for setting up 82551. This sets up both port A and port C on respective modes, that is 8th based on in and out, because port A is both are set as out using our 8th keyword. And then the 82551 is interacting with the ET GLCD module. Left half is CS1 and right half is CS2. There are 8 pages and 128 columns. There are 8 pages on both the CS1 and CS2 parts. Okay, moving on to the next slide. So moving on to the role of 82552 in this project. The 82552 is responsible for interacting with the keyboard, that is the ETKB module, which is actually organized as the key matrix, where we select the row we have to select, and based on the columns, the output is given back to the 8085. The port C is here to use used here to activate the row during this scanning. Let's consider actually we have used only PC0 in our project current here. In real we can use both PC1 and PC2 too, but for our project we are only considering two keys, that is the 001, the 00 and 01 keys. So for a slideshow we are not using any other keys, so that's why we are not giving any active signal to PC1 and PC2. This is just to prevent the extra T cycles here, because enabling them and looping through all the rows will in real actually cost us more T cycles and worse latency, a higher latency. So we are just using only the relevant ones. Only the PC0 we have used here and the rest are turned off. Okay, this is also visible in the code that I have written and attached with the video, and you can see, let's simulate something. Let's say the user presses the 05 key, then what will be generated? Because the active is the PC0, the active row is PC0, and the port is used to read the resulting active high column bit. Active high column bit means that the key pressed is high. That means the output that will be sent back to the 8085 will be this. There will be zeros and all the side, and PA5 will be 1 and the rest will be zeros. And now this PA5, this PA5 key, that 05 key can be read off easily by the 8085 using simple bit masking. And this is the layout of the actual ETKB module that we have used, and zeros and 1 key are here configured for interfacing the slideshow. And there is the functions performed we have already discussed, that we first select the row, then we read the key that is pressed, and we do the masks checking, and based on that, the 8085 decision logic decodes the key to select which place in the RAM we have to go and present a slide to GLCD, the GLCD module. Okay, and this is a simple user control graphical interface, nothing really too much here. Detailed working of ETKB module, we have already discussed how it works. And the ETKB module is a matrix where we select the column, then we send the active high signal, and then we read the resulting signal based on if the user has pressed the key or not. And that is the selected row is driven to port C, and the resulting active column is read back at port A. So it's only one row is needed active at the time in the slideshow project. We have simplified the logic by only monitoring one row and avoiding the extra T cycles by turning on reading another rows, that is PC1 and PC2. Okay. So we move on to the GLCD module. The GLCD module here is a 128 cross 64 pixel module, and you can see here it is it is divided into two parts. The CS1 controls the left, CS2 controls the right. These are chip select 1 and chip select 2. Okay, and each is 64 cross 64. The width and height are both 64 cross 64 module pixels for each chip. Here, the CS1 is a controlling chip, that is a KS08 or something. Okay, and the resolution I have to already explain, and the internal dividing is 64 cross 64. We have talked. Also, each screen is paged into 8 pages. As you can see here, each page is 8 pixel thick and 64 pixels wide. The columns are 64 and the rows within these are 8. Okay, and this row 0 is one page, row 1 is second page, and so on. So each screen has 8 pages. Similarly, CS1 and CS2. Okay, this structure is necessary to understand so that we can generate appropriate controlling keywords for the GLCD module. Here you can see the structure and how the flow in general of the GLCD module. First, we have to initialize the LCD, then we have to select the page, then we have to select the column, and then we display the data. In the LCD initialization, the configuration is already written here. What you have to do, with D equal to 1, the LCD is on, with D equal to 0, LCD is off, and the control words are sent using port C. You can which are this data is sent on port A, and all these control words are sent on port C of the 82551 PPI. Okay, and chip select 1 and chip select 2 based on our configuration, based on our need. In our project, we have interacted with both of them on lighting up, that is initialization. But for the display of data, we are only displaying right now on CS1 in our example. If one wanted to display on both, it is very simple to extend that by selecting both the halves. The RS1, that is this RS is to select the instruction mode, and R read write 0. Enable is 1. Also, the enable here is based on the low to high pulse. We have to give the high pulse to, then also the low pulse to actually latch on the data to the GLCD module, and that is the high to low control word is only registered by the GLCD module as a valid input. EN0, yeah, as it is shown here, EN1, then delay, then EN0, so that the data is latched in the input register. Then we select the page, and the selection of page is done with the last 3 bits, x1, x2, x3. The data is sent on port A again, and then the control words are sent on port C. Then column selection is done based on these 6 data registers, and the configuration is already written here. Then we display the data. The display data is again sent on port A, and with all the control words on port C. The control words are simple. The control words are always the same, and they change based on a need. If for displaying data, we will set RS1 and read write, and based on that. RS1 sets the data write mode, and read write is equal to 0 configures it to write mode. RW equal to 1 would set it to read mode. Enable is 1, and then we give delay and EN equal to 0 so that the data is latched and our ETGLCD module works. Display the data. For this project specifically, the port mapping and control signals are mentioned here. The GLCD data is sent on 00, that is port A of 82551, and GLCD control is sent on port C, that is 02 of the 82551 PPI, and the control word are sent on 8255103. These are the hardware connections of our actual 8085 kit. That can vary from kit to kit. This was taken out from the 8085 manual kit. As you can see here, the manual I have already shown the manual, and on the 82552 we are interacting with port A and port C again from 08 and 0A, and the control word is sent on 0B. These are available in the manuals of the 8085 kit. This can vary from kit to kit, so it is recommendable that you refer your manual for this. We have already talked enough about the hardware. Let's move on to the software design approach. The software design, the code we have written, the assembly code here initializes the hardware, both the hardware based on the ports and their configurations of 82552. Then we prepare the keyboard row selection, then we initialize GLCD, then we read the column through that row using the bit masking and wait for key input, and then we select the slide or the graphic that is already saved on the RAM of our clear nugget. Then that data is written to GLCD using the 8255. So talking of the initialization sequence, the 82551 is configured so so the data and control lines behave as output, and 8255, that port A is as input and port C is output. The code is visible here. These MVI A 8th, the accumulator is sent with 8th, and that this 8th is this 8th comes from the configuration of the 82551 PPI that is responsible for GLCD. The 8251 PPI set both the port A and port C to output mode, and that is sent to the GLCD control 8251 PPI. Similarly for keyboard we have set here. Okay, and then all this this GLCD on, these are control words for initializing GLCD, and these are control words for initializing the keyboard. Okay, and this depends on the module we are using, the module how it reacts, and based on that. Then the clear LCD, which is a subroutine, is pushed on the stack and run. The clear LCD subroutine runs, and we are handed over to the main loop. The main loop is reading the input keyboard sequence, and based on that it configures it bit masks through ENI, and then using the CPI we are jumped to a reliable part of the slideshow. If 01 key is pressed, then we will show square. JZ show square is a subroutine. This subroutine is responsible for showing the square on the GLCD display. On in this project we have only shown on CS1, not CS2, using 2 pages only, and then this if row 2 key 2 is pressed, then we show on the circle. Okay, and this loop runs continuously, jump main loop. This loop runs continuously until our program runs. Okay. Then the display rendering logic here, the show square logic is shown here, and the show circle. The show square logic clears the LCD, then loads the HL register pair with square data address and calls the draw shape CS1, and that is then jump to the main loop. The draw shape CS1 subroutine is also mentioned here, which controls 2 pages, page 2 and page 3 of CS1. Okay. The CS1, the left half is only responsible for rendering here. It is obviously easy to extend this to CS2 also. We will just need to add one subroutine more here for CS1 and CS2. Right now we are only rendering simple shapes, and it is easy to render on just on CS1. If we wanted to render real images on the pixel on the GLCD display using all the pixels, uh, we can just save the data on RAM and configure both our CS1 and CS2 to interact and show the output. The slide changes mechanism is based on the key press, the command C code, page column selection is done, and the data is written to the GLCD. Now we will move on to the demonstration of this slide. Once before that we should talk about the memory and the data organization too. Okay, the one thing that we should I have taken care of here from the manual. It was shown and it was written in the manual that the system uses 2600 to 27FF addresses for temporary use, and these are configured as the monitor program, and we should not really uh, try to override the monitor program. This can cause real issues. So instead we avoid this region, and there are some other subroutines too that are provided in the trainer kit, and we should totally avoid them, and I have totally avoided them. The data is written from 200H, and also if the frame buffer is used, then the buffer should totally try to avoid these addresses. Okay. So here is the demonstration video, and the demonstration you can see I have the GLCD module here and the ETKB module here. The ETKB module is connected to the J2 and the GLCD is J1. And this is our monitor program based trainer kit LED screen that is there, and the power is taken from the trainer kit to the GLCD module. The ETKB module doesn't really need any power here. This is because the signals are sent to the power and signals are only sent through the 8085 trainer kit only, the 8085 signal only. Okay. And SP is removed from here. I will run this code on the trainer kit using the monitor program and the monitor program instructions, that is a go instruction. Once I will execute it, and the execution on running the program, on executing the program, nothing will be shown on the GLCD screen. The project was just made like that. We can change that if we wanted to, as I have inputted the program. As you can see there, it is executing and there's nothing shown on the screen. But when I press the key that is responsible for the slideshow, the slide, we have to choose it through the ETKB module. I have pressed now the 00 key, as you can see, and the 00 key presents the square on the screen, and then I press another key which shows the circle on the screen. As you can see, these are left shifted because I am rendering on CS1 only, and you can see I can switch between them based on the keyboard input. I am switching between them based on the keyboard input. It can be seen more easily here in this too. This is a top view. you can see that when I am pressing the key here, the output on the GLCD screen is changing, and we can switch between these slides as much as we want, and the response time is quite good here too. Okay. Right now, our system was a very minimal system, and it was just a simple slideshow, and all the data was written already on the RAM. But for high profile and low latency interactive graphic system, like I was working on that ping pong game, I had actually written code for that too, the ping pong game, but it was a really long code to actually enter on the trainer kit through hand. It would have been convenient if I could somehow transfer that. So I have not really written the ping pong game there now, but there are some methods that can obviously increase efficiency and latency. They are like methods like frame buffer method that is very common in modern rendering too, in modern graphics rendering too. The buffer method, where the key is the input is pressed and the software frame buffer is kept instead of. Right now we are just flushing every input change directly to the GLCD. The GLCD, we are directly interacting with the GLCD RAM every frame, and there's no uh, interfacing with the software frame buffer. The software frame buffer method is to keep a copy of the display RAM on our uh, local 8285 RAM that is interacting, the CPU RAM, the microprocessor RAM, and it is easier to interact with the GLCD if we keep the same layout as GLCD pages and column, but we can change it if we do not want that. Okay, and we can edit the bytes in a local memory first, then this memory will be copied to the GLCD RAM. The convenience here is that the interfacing with the monitor or the interfacing with the display can really be a complex task. The GLCD is a very minimal and simple display. Yes, it has a bit of complexity in interacting, but for more complex interactions, or if you want to change the display, if you want to, let's say if you want to change the display, we do not want the GLCD in the future, then having a software frame buffer is a really optimum method. This is because we have a software frame buffer and we will just need to change some section of our code instead of completely rewriting every section of our code, as the flush step would be changed, the interaction, the interfacing with the GLCD, that code would need to be changed, and the copy of the frame buffer is done on GLCD, and that subroutine will be changed and everything will work as fine. The software frame buffer is a really good way where we can easily modify the drawing logic. We can control every part of it. We can control, we can also do partial updates, which is really good. We can only write on the important part on the screen which are changing instead of overwriting every part again and again. This is a really, we can do that on GLCD too, but interacting with the GLCD for every small task is a really induces a lot of latency. It is better that we first fix what we want to change and then we interact with GLCD. We should try to reduce our interactions with GLCD per frame as much as possible, because these are sent through wire lines and control lines, and the interacting with the GLCD RAM is a rather slower task, high latency task than directly interacting with the CPU RAM. For the conclusion and the what I have learned here are a lot of things. I've already worked with some modern graphic APIs like DirectX 11 and a bit of OpenGL exposure too. But and when I actually wrote this ASM code and the software part of it, the software part of it, and even the hardware part of it, it really exposed me to how this field, this graphics field, evolved from the older parts, from the older times to the modern times. While I was writing the software for especially the ping pong game and ping pong game, I really came across some really good methods, and I really understood how and why our modern APIs like DirectX 11 provide some functions and interfacing, parts like the draw one, the clear screen one. Like I could imagine what was happening behind those abstractions of these modern APIs too, because I was writing my own code and I was writing my own interfacing algorithms, or these are algorithms, a very minimal one and very basic one, but I was writing my own code and my own interfacing algorithms to interact with 8285, and that was really mind-opening to understand how we are interacting with the display, how the whole hardware is working. If from the perspective of a software too, it was really enlightening to understand how the hardware works, because it really helped me understand where the possible optimizations are, what can be optimized and what cannot be optimized, what are the limitations here, and why are these limitations. Um, this was really enlightening, and interacting with the graphics module with the keyboard, the interactive graphics project I've done was really interesting. I do plan to extend it for the ping pong game and writing some ping pong game on the simulator and interacting with it. That would be really cool to do. So thank you. I guess our presentation ends here on the slideshow based simple interactive graphic system on the 8085 trainer kit. Thank you.